In Chapter 12, we're going to learn about solids and some modern materials in the solid form. And there's a whole branch of research all about materials chemistry and material science. So there's plenty more, and we're not going to go too in depth, kind of just the basics, but there's a lot of really cool research about this, and it gets really technical and detailed. So if you want to learn more, go out and seek it. So in general, crystalline solids, as we mentioned last chapter, are solids that have an orderly geometric pattern. And their lattice points, or where their order is occupied by either atoms, ions, or molecules. Scientists study these materials using different types of light techniques, such as X-ray diffraction. What happens is that if the object has an orderly pattern, the X-rays can strike parallel to the molecules, and you can get a constructive interference pattern where we add amplitudes where the amplitudes are both positive or both negative, and destructive interference happens when we subtract the wave's amplitude. So you'll get this pattern that is related to the properties of the crystal. So Bragg's law helps us to learn what the structure and the difference between the different layers of the material are using Bragg's law. So Bragg's law says that the number, and that's just an integer, times by the wavelength of the light is equal to 2 times the distance between molecules times sine theta, where theta is the angle that they shine the light at. So you can get cool interference patterns based on how they are arranged, and so you can learn a little bit of information about the pattern of crystal structure. The crystal lattice, now there's a lot to learn about this. We're just going to talk about the minimum. We talked about crystal lattice with ionic structures. So when molecules are able to arrange themselves to really optimize their attractive forces, they're going to maximize those attractive forces. So get in an orderly way such that all of the cations are perfectly near an anion, and you get a nice little structure. So they're going to minimize energy by maximizing attractive forces. So that gives us that ordered crystalline structure. The arrangement is called the crystal lattice, and we've been referring to that with ionic compounds, but it also works with molecular and atomic solids as well. The smallest unit that shows a pattern is called the unit cell. You can see here a unit cell having one red atom in it and then a quarter of these white atoms. So for this unit cell, it would specifically, if we add up all those quarter atoms, we'd have one of the red and one of the white. So these unit cells are three-dimensional, like this one here in purple. It either has 2 or 3 layers depending on the structure in the compound. It can technically start with anywhere in the crystal because you're going to have the same unit cell that would be repeating. And then any particle is in the unit cell is a lattice point. The lattice planes are what connect the points. So here is one point, here's another, making those points as long as they're equivalent points. So here we have halfway through a white one, halfway through a white one, so that line would be a unit or lattice plane. How we classify crystalline solids depends on what kind of particles they are made out of. So all crystalline solids are ordered. And then after that, we are just going to classify it based on what kind of forces are holding the particles together. So if it is intermolecular forces made out of molecules, then those are going to be molecular solids. So individual molecules held together by IMFs. When it's made out of ions, so cation plus an anion, those are going to be ionic solids. And then atomic solids are made just of atoms. So we can have so single type of molecules. So we could have either non-bonding. So if we had like let's say a noble gas that was in the solid form, so literal atoms, if they're all made out of metals, then it's going to be a metallic compound. And then network covalent would be something like carbon, where we have carbon attached to other carbons, and we could have graphite or diamond, so that would be a network covalent, so all made out of the same compound. So this is basically nonmetals bonded together and with covalent bonds. They don't have to be all the same. So for example, silicon dioxide, SiO2, is a network covalent solid. Metallic is made up of just metals, so like gold or silver or sodium or whatever. And then non-bonding would be our atoms. That would be normally gases, so we say non-metal held together by dispersion forces, so think gases in the solid form. Okay, and they all have different properties. So molecular solids, think like sugar, carbon dioxide. So a literal molecule, when they are solidified, they melt at really low temperatures. When we have ionic compounds like sodium chloride or calcium oxide or whatever cation-anion combo, those are held together with a lattice structure, so they have very high melting points. Atomic solids are held together by atoms, so when it's non-bonding, like noble gases that are in the solid form, low melting points because they're held together only by LDFs. When we have metallic compounds held together, they're really strong due to their, they have that sea of electrons. Some of them have really high melting points, like platinum, titanium, those kinds of things, but some of them have lower melting points, such as like sodium. They're kind of more malleable. And then network covalent, they're held together with covalent bonds, so same type of non-metals, but covalent bonds versus dispersion forces. And so those, because they're held together with bonds instead of IMFs, they're going to have high melting points. So molecular solids are particles that are made up of molecules, individual molecules. So they're held together by IMFs, such as dispersion, dipole-dipole, and hydrogen bonding, depending on the polarity. Those tend to be weak, so they tend to have low melting points. Ionic solids are held together by ions, so of opposite charges. And because of that, they are non-directional, so they have that lattice structure. They are, because they're in all 3D, it's very strong, and so they have very high melting points, just like we've already learned about. And then atomic solids are particles made up of atoms. They could either be non-bonding, so held together by dispersion forces. Since they're literal atoms and not molecules, they're always going to be nonpolar. They don't have any kind of directionality. Metallic compounds are held together by metallic bonds, which tend to be strong-ish. And network covalent atoms are held together by covalent bonds, hence covalent. And non-bonding should be a hint that we shouldn't have bonds, we should have IMFs, such as dispersion forces. Metallic atomic solids, so just getting more into those atomic solids, they're held together by metallic bonds. Strength varies by the size of the metal as well as the charges. So things that have more electrons and are smaller tend to have a larger melting point than something that would be larger with a smaller charge. Non-bonding atomic solids are noble gases in the solid forms. And they're held together by dispersion forces, or LDFs, so those are very low melting points. We don't usually think of these as solids because they usually show up as a gas at room temperature. And then network covalent solids are attached by covalent bonds, and so they happen to be very strong because of the the sharing of electrons. They don't form a closed pack arrangement in the crystal because those bonds are specific, right? They're going to have a certain type of, it's not going to be like an ionic compound where they're just placed by differing charge. These are like arranged in with covalent bond type tendencies, like having a hybridization and a certain geometry. They have very high melting points, higher than 1,000 degrees Celsius, and this directionality of how they are arranged affects their properties. So we'll talk about carbon specifically and how that is affected. So let's talk about each of these as molecular, ionic, or atomic. So here we have gold, here we have ethanol, and then calcium fluoride. So gold is just made up of one atom, so that is an atomic solid, specifically a metallic atomic solid. So it would have, well, we know gold has a pretty high melting point. Ethanol is a molecule, so this will be if it gets into the solid form, it would be a molecular solid. And then calcium fluoride is made up of calcium and a metal or a cation, and then fluoride an anion, so a metal and a nonmetal, so this will be an ionic solid. We're going to spend a few slides just talking about different structures that carbon makes. So carbon's really cool because it can do a bunch of different things. In the case of graphite, we have carbons that are in a two-dimensional sheet. They are basically just carbon atoms covalently bonded together with sp2 hybridization. So each carbon kind of looks like this, bonded to another carbon, and then has another sp2. So we end up getting this trigonal planar geometry, and each sheet is just one giant molecule. And then each of the sheets, they're stacked together like this, like you can see here, and they're held together by London dispersion forces. They are slippery because they're only held together by LDF. So if you apply a force that is perpendicular to the sheet or parallel to the sheet, then you're able to make the planes glide without actually breaking any of the bonds. They have a really high melting point because to actually get the whole thing to melt, you do have to break some of the bonds. They are electrically conductive, specifically parallel to the sheets where electrons can flow in between the sheets due to the gap in the pi bonds. So graphite is a great conductor of electricity, which we don't really think about that when we think of our pencil lead. They are thermal insulators, so heat is not able to really go through them. And they're very non-reactive, which is good. They're used in batteries, and so you can provide a lot of current and electricity and energy without actually getting the molecules to react. So they're very, very stable. If we take graphite and we apply a lot of pressure to it, we can actually form diamond in that way. Diamond is the same structure as far as being all carbons, but it has 4 covalent bonds. It has sp3 hybridization, so it's instead of just bonded in 2 dimensions, it's bonded in all 3 dimensions. And each crystal is just one molecule, where before with graphite, it was each sheet was a molecule and they're stacked onto each other. One crystal of diamond is a full molecule. And so because of this and all of those covalent bonds in all the directions, it has a very high melting point because you're basically having to break all of the covalent bonds. Because of that, it's very hard and rigid, happens to have one of the highest, most hardness scale measurements. It is electrically insulated, so it's a great insulator of electricity because basically electrons cannot flow through it, but it is one of the best known thermal conductors, so it goes the opposite way of graphite in that way. And it's also very non-reactive due to the stability of all of those sp3 hybridized bonds. Now, if you were to take a graphene sheet and put it into a ball, then that is what is called a buckyball or C60. It is a 5 and 6 membered rings. So here's a 6-membered ring near a 5-membered ring of carbon, and it's wrapped around itself. So you get this 20-sided structure. It's called Buckminster fullerene, after the scientists who constructed it. And then they've been able to create other buckyballs similar to it with different types of amount of carbon. And these are just generally called fullerenes or buckyballs for short. Their properties, they are a black solid at room temperature. They're held together with IMFs via dispersion forces since it's very symmetric and nonpolar. They are soluble in nonpolar solvents because of that. And they can form solutions of different colors depending on what is around them, what kind of other compounds are there, and how big they are. If you took a graphene sheet and twisted it into 2 dimensions or into 1 dimension, you can create a nanotube. So basically we just take that sheet and fold it in, and we can get multi-walled nanotubes, and a lot of these are used in stuff like carbon nanotube bikes, and these are very strong materials. They are flexible because they're very thin in that direction, and very strong in this direction, so you can bend them around and manipulate them a lot. You get a lot of conductivity because they are like a graphene sheet, so they conduct electricity really well. They're, like I said, very lightweight because they're really thin and also just made up of carbon, which has a low molar mass. So they have a lot of potential for different applications. Moving on to another type of material, silica and quartz. So these are types of molecules that are made with, these are covalent network solids. So silicates are made up of silicon and oxygen, and sometimes you'll have aluminum in there as well. Glass is an amorphous form, so it doesn't have an order structure. SiO2 in its pure form is called quartz, and you can add impurities such as other metals to add color. In 3 dimensions, they're covalently bonded to 4 oxygens in a tetrahedral arrangement. So we write SiO2, but that's really the empirical formula, not the actual formula. High melting point, just like diamond, because of that covalent bond in all directions, and they're very hard materials. Polymers are a type of plastic. Now, there are lots of natural polymers and technically proteins are types of polymers in our bodies. There are also man-made polymers, and that's what we think of when we think of plastics. So polymers we take these small molecules called monomers, and they usually have double or triple bonds, and then we react them with each other, and these double bonds kind of break apart. The electrons in the double bond come and bond to a neighbor and form a single bond chain. So we take a monomer like ethene and make a polymer polyethene to make this long chain, and it repeats, and because of that they can be transparent and translucent. They are chemically resistant because you've already been able to react them with other molecules to give them a more stable structure. They can be great insulators of both electricity and heat. Because you can make them out of different monomers, they can have different densities and strengths, and we see that with our own plastics in the world. Plastic bags being one of the more weaker type, and then something like a jug being a lot thicker and more robust. They have elasticity, so if you apply some stress to it, they can go back to the original shape. When you heat them, they tend to soften. and rather than just melting, and then because of that, you can use them to make molds. So, like I said, there are natural polymers in the living and non-living environments. So like I said, proteins and nucleic acids are a type of natural polymer. So proteins are made up of amino acids, and then nucleic acids form DNA. And then you can chemically alter some of those natural polymers to modify them. Synthetic polymers are made in a lab from multiple different types of monomers, and you can use a variety of monomers that can be linked together in a pattern. So some fabrics, adhesives, and rubbers are examples of that. And then composites are materials made of polymers with additives. So graphite, the graphite you use in your pencil is made, you add composites to it to help strengthen it so it doesn't break as easily, because it tends to be very fragile if you were to apply any stress to it. So the composites are those. Polymerization is how we form polymers, so that's where we link the different monomers together. Basically, if they're asymmetric, there's going to be a head side and a tail side. So the head of one monomer will link to a tail of another. You could also arrange it so a head might react with a head or a tail to a tail during the polymerization. But more common than not is a head to a tail, and that would be more specific. And then this regular pattern gives strong attractions between the chains. And so you don't get as many random arrangements. So this is just a little slice of material science, or materials chemistry, but there's a whole lot more going on in the realm of energy, medicine, electronics, just so much. So it's really cool and interesting research you might be interested in getting involved in.